Our next speaker is Christian Delb, who will be speaking on DP minimal domains.
Okay, so first I would like to thank the organizer for giving me this opportunity to talk. I apologize for people who have already seen this talk. But yeah, so I will talk about DP minimal domains. So what is a domain? A domain is an integral domain or domain. I will use the same, both words. It's a commutative ring in which there are no non-trivial zero divisors. Equivalently, you can see it as a subring of a field, the fraction field or another field. We will study it mainly in the language of ring or expansion of language of rings. And what about what are the interaction between integral domains and model theory? So it hasn't been much studied as such as an object. So mainly because of this very simple fact that every NSOP integral domain is actually a field. So as soon as you have an element which has no inverse, then you can form this this chain of principal ideals which are included in one another. And because it has no inverse and because you can cancel those inclusions are strict. So you get NSOP SOP for this formula X belongs to Y. So for us, we will be interested in integral domains which are not fields. So we will be in the upper half of the classification. So the upper half, I mean, so everybody knows this this classification landscape. And so all the NSOP class, wait, put this in red. Okay. All this NSOP class will be out of reach, okay? So we will be interested so of course, in DP minimal ones, but also we can say little things about INP minimal and finite burden and finite DP ring. So if you recall here, the burden, so is this kind of notion of loose notion of dimension, which agrees with the DP rank in the NIP context. The burden is can define the NTP2 class. But yeah, so basically what we will use in this talk is that DP minimality is basically INP minimality and NIP. Okay, so for time integral domains, what the question is, what can be said about NIP or finite burden, finite DP rank, INP minimal, DP minimal, mainly integral domain? How does those combinatorial constraints translate into algebraic properties of the domain? So let's go through some conventions and notations. So I think everybody knows what an ideal is in a ring. You can form the radical of this ideal by looking at all the elements such that some power of this element falls in the ideal. Okay, and an ideal will be called radical if it is equal to its own radical. Prime ideal, okay, so this is okay. Prime ideal is an ideal such that the complement is stable by multiplication, and what we call the spectrum is the set of all prime ideal of R, and it's a topological space, and it's a poset for the inclusion, and the order type of this poset gives information on the the ring, the domain. Domain is local if it has only one maximal ideal. Okay, so this is classical. And in this case, you have what is called the residue field, just the quotient of this ring by its maximal ideal is a field, and so we have also the notion of residue characteristic. And then a valuation ring, it's an integral domain whose set of ideals is linearly ordered by inclusion. And in this particular case, there is a correspondence, which is well known, between valuation rings of some k, so that the fraction field is k, and the value and valuations on k for any field. Yeah. Okay, so let's go through some basic results on tame domains. So something which was observed by Pierre Simon quite a long time ago when he told me this, and it was an interesting fact. Very easy. It's just a very simple application of an IP, but you prove that in an integral domain, the maximal length of an antichain of prime ideals is bounded by the VC dimension of this formula here. In particular, in an IP domain, you will have also that you have so an antichain of prime ideal is just a set of prime ideals which are not comparable to each other. Okay, and so this is finite in an IP. The maximum length of this is always finite. In particular, there is only a finite number of maximal ideals in an NIP domain. So can also do the same, a similar argument. It's a bit different, but you get the same result for finite burden. You get that the burden is actually bound of this maximal length of an antichain of prime ideals. So already what we know for an INP minimal domain, which means burden 1, that the spectrum will be linearly ordered by inclusion. Such domains are called, in the literature, it's called local treed. Local because it's local, and treed means just that the spectrum is ordered like a tree. So if you have a tree with only one maximal element, it's just a linear order. And then consequences of this, of the fact that the spectrum is linearly ordered by inclusion, is that all the radical ideals are prime, and there exists a constant such that for all AB, either B to the n belongs to A or A to the n belongs to B. So of course, this is also true. This corollary also holds for DP minimal, because every DP minimal is INP minimal. But can we say a bit more for DP minimal integral domain? So let's go through some examples. Yeah. So every definable subring of a DP minimal ring is DP minimal. So we have all the classical valuation rings of our favorite DP minimal domains. So the ZP, it's a DP minimal domain. And if you take the field of Hahn series, you look at the valuation ring, then you get DP minimal domain, provided the field itself is DP minimal. So you get that this kind of rings are all DP minimal domains. And if you take the hyperreals and you look at this set of bounded elements, then this also is DP minimal. I mean, it's the same. It's also a valuation ring for the infinitesimal valuation. And then, so a natural question arises when we know this famous fact from Wood Johnson that any DP minimal field is either algebraically closed, real closed, or admit a non-trivial definable incident valuation. Do we only get valuation rings when we look at DP minimal domains? And so the answer is no, of course. It's not obvious, but it's easy to construct. Let's look at an example of this. So for instance, you consider the Hahn series over the algebraic closure of a finite field with a value group Q. And you can define this little ring. It's called the A plus M construction. It's just you take an ideal of the valuation ring, and you add the subfield of the field. So Fp plus this ideal of element of valuation greater than 1. It's a definable subring of K, so it's DP minimal. So it's a local ring of equicharacteristic P, so okay. But it's not a valuation ring because you have these two ideals. So if you look at Fp plus the element of valuation greater than or equal to 2, then you have T in this one, but T is not in this one. And you have, what is it, T to the 3/2, which is in this one and it's not in this one. 3/2 is not in this one. Okay. So it's not a valuation ring. A recall valuation ring should have every pair of ideals should be comparable. So we also have an example in mixed characteristic. I won't talk too much about it. I will come back on it later, but basically you do the kind of the same construction here. You don't have actually a field, but this set, the set of sums, okay, of this ideal, the ideal of element of valuation greater than or equal to 1, then it forms a ring, and it's a local ring of mixed characteristic, which is not a valuation ring again. What about, so we have an example in characteristic, in mixed characteristic and in equicharacteristic P. So what about in equicharacteristic 0? And in this case, it goes smoothly. So it's even true for INP minimal domain. So if you have an INP minimal domain of infinite residue field, it's a valuation. So in particular, every INP minimal domain of equicharacteristic 0 is a valuation. Okay. So what can we say more about the DP minimal integral domain? So there is this notion, quite an old notion of a divided ring. Akiba actually called it, what was it, AV domain, probably for almost valuation ring, something like this. So it's a ring in which every prime ideal is comparable to every principal ideal. And so you can see here you have this direction, right? So this implication. If you are a valuation ring, then you are divided, and if you are divided, you are local treat. Okay. And so what we know is that INP minimal rings are local treat, but what we proved with Yatir is that every DP minimal domain is divided. So this is not a trivial fact. We had to use all the machinery that I will try to define a bit later. But yeah, so here we have DP minimal. Looks like a small increasing, but for now we have this. But we cannot expect much more. I mean, we know that all of them are not valuation. Okay, so let's go a little deeper. much time do I have left? Okay. So if you work with integral domains, you will encounter what is called an overring. So an overring, it's a subring which is in between R and its fraction field. Overring and frac R. So easy way of getting such overrings is by localizing. So localizing is when you take a set which is multiplicatively closed, then you can consider all the if a set is multiplicatively closed, then you can consider an overring in which you have inverted all these elements. And the most famous example of this is for prime ideal. You can localize by the complement of the prime ideal, and I will denote it like this. Okay, and the nice thing about this is that it's very well behaved according to the burden and the DP rank. So what we proved is that if you have a multiplicatively closed set which is definable, then the localization preserves the burden. And if it's externally definable, then externally definable you can deal with such set in DP minimal and in general NIP structures. So you can also consider them. It will also preserve the DP rank, the DP minimality, etc. For those who would not know, externally definable means that it is the trace of a definable set, but with parameters in an elementary extension. Okay. So let's look at a very nice phenomenon that we encounter in DP minimal domains. So if you take an element in a domain, then there exists a unique ideal PA such that PA is maximal with the property that PA does not intersect the power of A. And so PA is prime, this is easy to show, and externally definable. And this is, it's not very hard to see, but it's a very nice fact. PA is prime and externally definable. So it's externally definable because basically you can write it as a junction of formula, and which are uniformly, it's a uniformly type definable set. And this gives externally definable sets. And what we can say about PA a little bit more is that PA is the maximal ideal prime, maximal prime such that A doesn't belong to PA. And then a nice fact is that this kind of prime ideals are actually very, very useful, because every prime ideal can be intersected by, is the intersection of such PA. And in particular, we have that every prime ideal is externally definable in a DP minimal domain. And then applying what we had just before, we have that if R is DP minimal, then the localized, the overring RP is DP minimal for any prime ideal. So for those who know, those ideals are the goldmine ideals in the literature. And we have this nice fact, like PA is strictly contained in the square root of A. And then, you know, A doesn't belong to this one, and it does belong to this one. This one is the maximal, the minimal prime. So it's prime because radical ideals are prime. minimal prime such that A belongs to it. Okay, so already we can do a little proof for this short talk. We will prove this. So if you start with the DP minimal domain and you take a non-maximal prime ideal, then the localized is a valuation ring. So first, P is radical because it's prime, so it has infinite index in R. Because for any element with it, so we assume that P is non-maximal. So this is non-empty, and the set of powers of B will be in different classes modulo P. So now, because R is divided, P is PRP. So PRP, what is it? This is the maximal ideal of RP. When you localize, you get a local ring, and here in RP, the maximal ideal is PRP. And because it's divided, it's also P. It's the same set. So in particular, in here, the maximal ideal has infinite index, and so it's very nice, and we know that RP is DP minimal because of what we had before. So it's a DP minimal integral domain with maximal ideal, which has, or let's say with infinite residue field. So it's a valuation ring by what we had before. Okay. And then we have a characterization of DP minimal valuation rings. So which DP minimal valuation rings? DP minimal rings are valuation rings. So we have an if and only if, which is R is a valuation ring if and only if either as R as infinite residue field or R as finite residue field, and the maximal ideal is principal. And so this current condition is actually not weakenable. So in this example, we had before the maximal ideal is actually P and P square root of P. So it's not principal. Okay, we have a little more. Okay, I should finish sooner. We have a little more results in equicharacteristics. So there are many equivalents for a ring for DP minimal integral domain to be a valuation ring. It's equivalent to many properties, but to finish on this. So there was this result in 2019 by those two guys, Eki and Kalfala. And they proved that in the bounded hyperreal and bounded hypercomplex. So the hypercomplex is basically the complex with the norm, with the real norm map. And then you take a neutral power. And so in these two rings, there are no three consecutive elements. And so they used a lot of tools that I didn't really well understood, but it seems to us that it could be something else that was behind this, and it was the case. So what we did is that first we translate this property. I mean, they did it also. This property of having no three consecutive elements means that PA is densely ordered by inclusion, and it's also equivalent to PA is different from square root of B for any AB. And this condition here, if you look a bit closely, it's actually a condition about a type definable set being equal to a V definable set. And so this is the idea behind the generalization we have. So let me state it. Let D be a capacitor domain and R a V definable local subring. whose prime ideals are linear ordered, then R as property star. Okay, so it's really a matter of kappa saturation, and basically it's a matter of compactness. So if you assume that it's not true, then you will have equality of two sets, one which is type definable, the other one which is V definable. And so you get some finiteness and contradiction. And we get more of this kind of phenomenon because in a valued field case, it's also a matter of saturation in the valued group, and of course we have this consequence, the analog for ZP of the result. Let me end with some questions, open questions. So our only examples of DP minimal domains are definable in a DP minimal valued fields. Are there other kind of examples? So, and do we have some good theory of integral domains which are not valuation ring? This is an interesting question also. Is if R and gamma are DP minimal, is it also the case for the positive Hahn series over this ring? Because here R is a ring. And then we can ask also this question. I mean, everything we have proved in the direction, you take a DP minimal thing and you look at the algebraic consequences. Do we have the converse of this? So this property implies that the ring is DP minimal, so it's still open. Okay, so thank you very much for listening. And if you have any questions.
Thank you, Christian.